So in the last, we're trying to do everything with phases instead of the time domain and operate all in the phasor domain. We know resistor R is still a resistor R in the phasor domain. An inductor, L, became J omega L. And we had to finish by saying, well, what do we do with the capacitor in the phasor domain? How is the phasor voltage on a capacitor, this complex number representing an amplitude and phase, related to the Phasor current? So I said, well, here's your complex exponential voltage, your complex exponential current, and I know in the time domain I equals C times dV by dt. So I substitute that in, I cancel out, and so I end up with this J omega down here. Quiet, please. In the middle there, yep. Yep, you, there. Thank you. Now I can cancel out the e to the j omega t's from both sides. And I get em e to the j theta I equals j omega c times vm e to the j theta v. Well, that's my phasor current. And that's my phasor voltage. So in fact I get I equals j omega c v, or V equals 1 on j omega c times I. So we're going to now replace capacitors. If we want to do Ohm's law type stuff and KCL, KVL everywhere, the capacitor becomes 1 on j omega c. So I have R j omega L for inductors, 1 on j omega c for capacitors. And that shouldn't be too surprising that it's the inverse of what we do for an inductor, because of the dual roles that the current and the voltage play for capacitors and inductors. So that's the key. I equals j omega CV. So that's how the phasor voltage is related to the phasor current. So if you plotted the current and voltage waveforms, you could see that this time the current is leading the voltage by 90 degrees, whereas for the inductor the voltage led the current by 90 degrees. And that's also demonstrated in the complex plane, just in terms of the phasors V and I in that figure there. So can you use it now? We've done that. Can you use it? Example 8.7, given a voltage, Vt equals 100 cos blah, blah, blah. I apply it to a 100 microfarad capacitor. Whoops. Can you find the resultant current? Now you could just do that in the time domain. You could immediately just go I equals C times dV by dt. But just suppose you can't differentiate. Now you've got a way to do it without differentiating. You use this relationship that we've just derived, I equals j omega CV. So you take your voltage, convert it to a phasor. Then you can use this relationship here to find the current phasor, and then you convert that back to the time domain. Still, I think on the leaderboard, you can't separate 3 people at the top on 49, I think. I want more chocolates is a very popular answer at the moment. Okay. Oh.
Is there an error with your magnitude with the A?
Which one?
Answer A. Is it supposed to be 3.14?
In my answer, A.
Yeah, is option A meant to be 3.14? Because it's 31.4.
It was just meant to be some wrong answer. So it doesn't matter. You can. I tried to do something that looked like it might be right in terms of the angle.
What are you talking about?
I did make it precisely 90 minus 15 in terms of the angle. But all right, locking now. 52 out of 72 said B. 3.14 cos 314t plus 105 degrees. So here's first you've got to get V, that's step one. 100 at angle 15 degrees, reading off the amplitude and the angle. Secondly, the phasor I is related to V through I equals j omega CV. J is J, omega is 314, the capacitance 100 microfarads, which is 10 to the minus 4. J is 1 at angle 90. Straight up, 1 at angle 90 degrees is J. So that's where the 90 comes from. Should we run for it? It's Big Dog. He's coming to get us. So that is 3.14 multiplying amplitudes. I add the angles, 3.14 at 105 degrees. Convert back to time domain. So it's 3.14 cos, same omega, plus 105 degrees in amps. So most of you were able to get that, which is great. Any questions? Here was a good entry. This won my favourite prize. This was Norbert Nadal when he was a little bit older. The one when I showed you one, Norbert Nadal was when he was, he looked a little bit like Jon Snow. Now, when he got older, he looked like Ned Stark, which is reasonable. Now, everybody voted for that. I have no idea what any of it meant. No idea, but it won the popular vote. So there you go. I had to give an award to it because it won, but I didn't get it. What's something to do with what? Polka dots or something? Polka dots? Okay, so we've calculated the ratio of phasor voltage and current for resistors, capacitors and inductors. That ratio is called the impedance. So now we're in the phasor domain. We don't call it resistance, that's just for resistors. The generalized versions, these J omega L's, 1 on J omega C's and R, they are called the impedance. It's much like resistance, except it's complex. So Z equals V on I, these ratios of the phasor voltage and phasor current as a magnitude and a phase. The real part is called the resistance, and the imaginary part is called the reactance. So we have a resistance plus a reactance. Okay. It's the heater, I think. We know impedance is frequency dependent. It's frequency dependent. We had J omega L, 1 on J omega C. You change the frequency, now the impedance changes. And that's what gives us all the flexibility to design all these different circuits to do different things, to respond to certain frequencies in different ways. That's why capacitors and inductors are so useful. So here are the basic impedances of single elements, R, J omega L, and 1 on J omega C. Note that we don't call Z the impedance of Phasor. The phasor represents voltages and currents. So Z's complex, but the phasor is about the voltages and currents in the circuit. Z's just a complex number, which we call the impedance. KCL, KVL, they're both valid in the frequency domain or in this phasor domain. Series parallel combinations of impedances are just like resistances. So if I have a capacitor, inductor and resistor in series, I can just write down the impedance. Treat them as if they're all resistors in the old world, but now they're complex quantities. So that the series and parallel combinations I can do in the complex domain. One on impedance is called admittance, and that's the analogue of conductance. You can probably work this out. Why would you prefer resistance? Let me get ready for it. I did warn you. Thank you, thank you. I've got to tell you, you know how those slides about how people should properly respect me? Is he here? Yeah. So I was walking around Chadstone the other day with my family, and out of nowhere, someone came up and started bowing to me in the middle of Chadstone. There he is. There you go. Jamie's son. He called me Jamie's son. And then just stood up and walked away. And my family, my wife and 2 kids, they're all going, what's going on? I just walked off. Just someone from uni. They all treat me like that, you know. Life has never been so good at home, I'll tell you. The respect I'm getting now. Oh, Dad, that was amazing. By the way, I did tell you don't need to sit the final exam, didn't I? It's locked in. Locked in, 100%. So I want to look at the equivalent impedance of this series combination of a capacitor and an inductor. So it's just the sum of the two things. But what is Z equivalent? What is Z equivalent when omega equals 1 on the square root of LC? It's not a melts. Just eternal fame and glory when you yell it out. So I sum them up. What's 1 on J? Minus J. So I could take the J out and write that as omega L minus 1 on omega C. And I want to substitute in this value of omega. What do I get? What do I get? What is it? Say it.
Is it 1?
No. Say the other one. 0. Yes! I mean, you just have to plug in omega. You get J outside of root 1 on root LC times that is root L on C. Minus 1, that's root L on C, which equals 0. I can have those two things there. I put a voltage across it, the current will be infinite. They kind of cancel out. I'll show you something that's similar, but in a mechanical version of this. You've seen this, I assume. There's a bridge resonating. Something excited the resonant frequencies in the bridge. Oh, we'll watch the car. So, omega equals 1 on root LC is the resonant frequency for that circuit. It's called the resonant frequency. If I excited the circuit with a sinusoid of that frequency, it would start to resonate. The energy would transfer between the capacitor and the inductor, the capacitor and inductor, and the natural frequency that does that is 1 on root LC. So if I excited that frequency, bang, boom, bigger and bigger fluctuations, bigger and bigger currents flowing in that circuit. That's a resonant frequency. There's one of those in every radio receiver. Choose 1 on root LC to be 774 kilohertz, for example, and tune into your radio station. In your classic radios, when you're tuning, the old ones, you're adjusting the capacitance or you're tuning the inductance and you're changing the resonant frequency. Okay? So effectively you're going to filter that particular frequency of interest and the other ones will be filtered out. So that's a resonant frequency. The impedance of the series combination can be 0. Absolutely can be 0. Could be useful for the exam. Could be, might not be. I don't know for sure. So in this example, it says, determine the equivalent impedance of the network shown if the frequency is 60 hertz. It's again like a bit of a series combination here. Oh, there we go. Even better, crapjack. Series combination, but now we add a resistance in as well. So what do you need to know? Well, firstly, what's omega? Omega equals, does it equal 60? No, 2 pi times 60, 2 pi f. So 2 pi f, which equals 120 pi radians per second. So that's your omega. And I know the equivalent impedance of this thing will be Z equivalent, will be R plus J omega L plus 1 on J omega C. And I just have to plug in the values of omega, R, L, and C into that. And I'm going to assume you can do that. I would get 25 minus J 45.5, ohms. So 25 minus J 45.5 ohms. Overall, if I said to you, does this load, does this equivalent resistance look capacitive or inductive? Does the equivalent impedance look capacitive or inductive? Well, is it plus J or minus J? It's minus J, that's capacitive. So if I had to replace that combination with just a single, with two components, I could do it with a resistor and a capacitor of the right value, because it's negative J. Remember, 1 on J is minus J. So capacitors correspond to negative impedance. So there we go. Let's up the frequency a little bit to 400 hertz from 60. So the only difference is now that omega equals 800 pi radians per sec, and I again plug in, R plus J omega L minus J on omega C, and I would get that Z equivalent is now equal to 25 plus J 42.3 ohms. Now does it look capacitive or inductive? It's a plus J, that's inductive. So overall it's now starting to look like a resistor and an inductor, the combination. Somewhere in the middle, it's going to be, this equivalent impedance is going to be just 25 ohms. When's that going to be? 1 on the square root of LC. At the resonant frequency, all I'm left with would be R equals 25 ohms when omega equals 1 on root LC, and it must be somewhere between those two frequencies we've just done, because the first frequency, it was negative J, the next frequency was positive J, it'll be 0 somewhere in between. That is the resonant frequency for this particular circuit. So that's a series resonator. You can also have a parallel resonator where your inductor and your capacitor are in parallel, not in series. So I want to just check that on one where the numbers are a little easier. Oh. So let's make sure. Easy numbers. Angular frequency 1 radian per second. I've got a 1 ohm resistor, a half a farad capacitor, and a 1 Henry inductor. And I want to know what is the equivalent, what is Z equivalent, looking in there. So exactly what we've just done, but with easier numbers. And that's the next melts question. Could be the decider. There we go. What is Z equivalent in ohms? I think some people forgot that it's minus J for a capacitor. By the look of the responses. Starting to correct now. Right, 10 seconds. 10, 9, 8, 7, 6. Why is 1 over j equal to negative j? Times top and bottom by j. J squared is negative 1. J is the square root of minus 1. So is that, I mean, just to... So I've used everywhere here. 1 on j is minus j. So that's why capacitor is 1 on j omega c, why it's negative. Okay. So this is okay. R's 1. What's omega times L? That's 1 times 1. That's 1. What's omega times C? It's a half. 1 and a half is 2. One minus j ohms. And I guess 90% of people had that answer by the end. So I'm assuming that's okay. All right, these phasor diagrams, this annoys me a little bit. I mean, you can add complex numbers. You can add complex numbers on the complex plane. It's like adding vectors. 1 plus j added to some other one equals that one. All right, you can add complex numbers on a diagram. That's all this says. They're like vectors. Yes, things are getting pretty serious. This is it. I thought this one was quite good. Not many other people did, but it's in the node. There we go. This says phasor diagram example, but let's say it's another example of how you analyse circuits with phasors. We have resistors, inductors, capacitors. We're told an initial voltage is a cosine. I want to find the current and find VR, find VL, and find VC. Basically, analyse that circuit. Now, if you could have done Kirchhoff's voltage law and tried to, get a differential equation. You would get a second-order differential equation, and you could have gone through that technique to try to solve it. Here, we don't need to. We can just use complex arithmetic. So what would be the first step? Well, you convert your inductor and your capacitor to their equivalent impedance at omega equals 377 radians per second. So you first find omega. .377 radians per second. This L looks messy, 15.92 millihenries, but well, firstly, what's the impedance of the resistor? Just the resistance, which is 4 ohms. What's the impedance of the inductor? Well, it's J times omega times L. There's L, there's omega, plug it in, and nicely here, it's J times 6 ohms. The inductor was chosen at a horrible value so that the impedance would come out at a nice value. What about the capacitance? Well, we've said that's minus J on omega C, and that turns out to be minus J 2 ohms. So there's your first thing you do. Do all the J omega L's, 1 on J omega C's all over the network. And from now on, these are the only quantities we have to worry about. These ones we've just found here. What's the phasor voltage? Well, I read off the amplitude there, 12 root 2 at angle what? 0. It's just cos 377t plus absolutely diddly squat, so it's 12 root 2 at angle 0. If they were resistors, how would you find the current? You'd add up the three resistors in series and go Vs divided by R. That's all we do now. Exactly the same approach as you would have taken if everything was just a resistor. That's the key. So this is 4 ohms. That's J6. That's minus J2. What's the equivalent impedance? What is it? 4 plus J4. Yep. 4 ohms, 4 plus J6 minus J2. So 4 plus J4. Is that okay? I hope so. In polar form, what's 4 plus J4? It's an easy one to convert. 4 root 2 at angle 45 degrees. The real and imaginary parts are the same, 45 degree angle. How did I do what? I just converted from Cartesian form to polar, but it happens that 4 plus J4 is an easy one to do. Because if I have two sides at 4, I know square root of 4 squared plus 4 squared is 4 root 2, and the angle has to be 45 degrees. It's tan inverse 1, which is 45 degrees. That's just one of the easier ones to do. I is just Vs divided by Z equivalent. How much current's flowing? Well, the voltage source divided by the equivalent resistance that it sees. Just everything's complex. So 12 root 2 at angle 0 degrees with our Vs on 4 root 2 at angle 45 degrees, which equals 3, not root, 3 at angle minus 45 degrees. So I know the current, 3 at minus 45 degree amps. What's VR going to be now? The phasor voltage across the resistor is 4 times the current. What's going to be VL? J6 times the current. What's going to be VC? Minus J2 times the current. You just multiply the impedance by the current to get the voltage on each individual component. So we found this I. This was 4 ohms. This was J6 ohms. And this was minus J2 ohms. And the current I we just found was what? 3 at angle minus 45 degrees amps. So therefore, VR equals RI, which is 4 times 3, what's that? 12 at angle minus 45 degree volts. VL is J6 times I, which equals what? What's J6? 6 at angle 90 degrees. So you could say that's 6 at angle 90 degrees multiplied by 3 at angle minus 45 degrees, which equals 18 at angle 45 degrees. What's VC? Well, that's minus J2 times I. What's minus J2? 2 at angle negative 90. Thank you. 2 at angle negative 90 by 3 at angle 45 degrees, at minus 45 degrees, sorry, which equals 6 at angle minus 135 degrees. So I found the current, all of the voltages in the phasor domain, and it's pretty easy to go from the phasor now to the time domain. I know the amplitude and the phase, and the rest is cos omega t plus. Now this phasor diagram business just says that, let's suppose, what should I know about VR plus VL plus VC? What should VR plus VL plus VC be equal to? VS. Kirchhoff's voltage law around that loop. So look, let's suppose I wanted to show that. You might get a diagram like this, which is handy for angles and things. So there's VR. I'm going to add on VL. I haven't added it yet. And there's VC. So let's add them together. 1 plus 2 plus VC. And what I get left with is this real thing along the line there, 12 root 2 at angle 0. That's phasor analysis. Yes, I can add them in the complex plane. I'd prefer to just add them up myself, but you can add them in the complex plane. Often past exams will want you to do some pictures like this, but I don't like it, and I wrote this question this year, so you don't have to. Yes. I don't, to be honest, see the point. Well, I catch my breath and have a chat. I'll show you a little video about the Bionic Eye. We talked about the cochlear implant. Here's a Bionic Eye.
Vision Research and Technology. Monash Vision Group is a collaboration between Monash University, Grey Innovation, Minifab, and Alfred Health. We aim to develop a brain visual prosthesis to help people who are blind or vision impaired. Let's start with a description of how human vision normally works. When light from an object hits the retinal cells in the eye, it initiates chemical reactions which ultimately result in the generation of electrical impulses in nerve cells. These cells form the optic nerve that runs into the brain to arrive at the primary visual cortex. The primary visual cortex starts the processes which allow us to interpret light as images, which form our vision. If parts of this pathway don't function properly, a person can become vision impaired or blind. This vision loss can be due to a disease, genetic defects, abnormalities of the eye, or physical trauma. Some of the causes of untreatable blindness include macular degeneration, glaucoma, and diabetic retinopathy, amongst others. Monash Vision Group aims to develop a brain visual prosthesis to help people affected by these conditions. Direct stimulation of the primary visual cortex may offer advantages over other approaches, including more precise replication of foveal vision, which allows us to see fine detail, compatibility with other treatments directed within the eye itself. It may even help patients with damage to the retinal cells or optic nerve. The implant will comprise materials that are biocompatible and safe for use in the human body over extended periods of time. This reduces the risk of the body's immune system rejecting the implant. Optimization of implantation methods by our skilled surgeons will also reduce risks to the patient both during and following surgery. Monash Vision Group's brain prosthesis is designed to mimic the human visual pathway. A small digital camera, similar to those used in mobile phones, is mounted on spectacles. This performs the function usually fulfilled by retinal cells to convert light into electrical impulses. Scenes are captured by the camera as video images. These video images are transmitted to a processing unit which extracts the critical features of the scene. The processor uses intelligent algorithms to create a signal for transmission to the implant. The patient can select specific algorithms to optimize vision for different environments. The The signal is transmitted by a wireless communication system through the skin and skull to the implant in the primary visual cortex. This results in activation of an array of electrodes that have been surgically implanted. These electrodes stimulate groups of neurons to produce the perception of brief flashes or spots of light known as phosphenes. If enough phosphenes are evoked in a particular pattern, some features of the scene will be perceived by the implant recipient. Although the implant will not produce high-definition vision, Monash Vision Group aims to provide enough visual information to assist the recipient in performing daily activities, such as navigating familiar environments, like their homes, and to recognize the presence of people and objects around them. This is only the beginning of a long-term goal to provide useful, high-quality vision for the blind and vision impaired.
There you go. Good project. Maybe you can do a summer research project on it in coming years. So here's our, essentially the problem-solving strategy with this. If you've just got one frequency in the circuit, that's fine. You do this J omega L, 1 on J omega C everywhere. I'm not quite ready to go yet. So I'm going to need 10 minutes, all right, till 6. Otherwise, I have to come in on Monday morning and do it. So let's try and finish it off tonight. You replace each circuit element by their impedance. You analyse using standard circuit analysis techniques. And at the very end, you can convert your phases back to the time domain. And that is a pretty easy step. So if you had to calculate all the voltages and currents in this circuit, what I should say is some of the work's already been done, right? Because we've already got everything converted to its impedance. That just says already minus J4, J6. I don't even know what the frequency is here. So some of the work's already been done, but if it hadn't been, you'd have to convert everything to its equivalent impedance at the particular operating frequency. But that part's been done. Now, if you had to find all of those currents and voltages when everything was just a resistor, could you do it? What would you do? And if you can do it, then you can do it now, because you follow exactly the same procedure. So I did have this as a MELTS question to find the equivalent impedance. Now I've opened it just for those who want to have a guess. You're welcome to. I don't know if there's a chocolate option this time. So looking in there, and I say find the equivalent impedance. What can you tell me about the 8 ohm and the minus J4? They're in series. And what are they with this inductor? In parallel. And then it's in series with 4. So exactly as you would have for resistors, I could write this as 4 plus J6 in parallel with 8 minus J4. And it's the same formulas for combining. So this would be 4 plus, when I've just got 2 in parallel, it's the product on the sum. So it would be J6 times 8 minus J4 on J6 plus 8 minus J4. And then maybe your calculator will do it, or you can work away, rationalise the denominator, or realise the denominator, whatever your favourite technique is, and you can get your answer. Keep in mind, I've got the full solutions in the notes that I put up afterwards. So all the details will be put online. But that's just calculations. That's complex arithmetic. I want you to get the idea of the approach. Once I had Z equivalent, what's I1? Vs over Z equivalent. Ratio of 2 complex numbers. I've just found that one. I'm given Vs there. Once I had I1, well, what's V1? V1 could be, I could do Kirchhoff's voltage law around there and write it as Vs minus 4I1. As I said, whatever you would have done if they were just resistors. What would I2 be then? What's I2? Just in terms of the phases. V1 on? V1 on what? J6. V1 on J6. Voltage across a J6 impedance. The current is V1 on J6. What would be I3 in terms of some of the things we've already found? What about Kirchhoff's current law at the top node? I1 minus I2. Excellent. And what about V2? Voltage across that? I3 times minus J4. Just as you would have done before, but you've got these pesky complex numbers to deal with now. But that's it. That's the beauty of this impedance and phasor stuff. Standard circuit analysis, complex numbers, instead of differential equations, trigonometry, causes and sines floating around all over the place. This is much more convenient. There was one. Another one. Maybe it happened to you. So I want to finish. This is another $100 book voucher for the first solution I get. You can now, this was put up in the first lecture, and I said you'd be able to analyse it by the end. You can now do it in the phasor domain. Because what I want to know is, if the input here, the phasor was V in, the phasor was V out, what is the absolute value of V out divided by the absolute value of V in? Because it's the ratio of the amplitudes. Both of those, by the way, are functions of frequency. This is called the gain of the circuit, and it's a function of omega. Now, we already hinted that's a bandpass filter. The gain for low frequencies will be low, the gain for high frequencies will be low, and the gain at a particular frequency somewhere in the middle will be high. So it passes things in a certain range. Well, how do you prove it? Well, you just do. Instead of C, you put 1 on J omega C there, you put 1 on J omega C prime there, and you do your circuit analysis, use the golden rules for the operational amplifier, but everything now depends on omega floating around the place. Complex currents and voltages, things depending on omega, and at the very end, absolute value of V out divided by the absolute value of V in, and you fully characterise what this thing does, what this device does. So normally there's a book voucher for a nice presentation of that solution. Sometimes someone comes down right now and hands me the solution. I'm not sure if that'll happen at 5:57 on a Thursday night. That's all. On the Facebook poll, the things that you wanted to do next week, for those who voted, very clear. Work through a past exam paper. Second was tell you about this year's exam. And third was skip Monday's lecture so I can sleep in. So we'll do all three of those things. It'll be on Wednesday and Thursday. No lecture on Monday.